All right, in this video, we're going to talk through some periodic trends questions. These are all from old AP exams, so you get a sense of the types of questions that you might need to answer involving properties of atoms and periodic trends. So this one, write the electron configuration for the zinc ion. So first I'm going to write out what it would be for neutral zinc, and I'm going to use the noble gas shortcut, which is okay. So I took the previous noble gas was just argon, and I'm in 1, 2, 3, 4, in row 4, and then it's 3d10. So that's neutral zinc. And so the zinc ion, I'm going to lose my valence electrons. And which electrons are valence? It's the ones in the outer shell. So that's these ones. So I'm going to get rid of those 4s ones, and then here is my electron configuration for the zinc ion. And the question says, which species zinc or zinc ion has a greater ionization energy? Justify your answer. So this is where, you could always make a T-chart is always like a good strategy for trying to make a comparison. So if you look at your electron configurations, like let's look at how many, they're both zinc. So they both have, how many, 30 protons. Okay. And if you look at neutral zinc has 2 valence electrons. So that means everything that's not valence is core. So it's got 28 core electrons. So if I'm trying to find the effective nuclear charge, should clarify what I'm doing here. So if I find the effective nuclear charge, it's my protons minus my core electrons gives me the effective nuclear charge. So it's +2. Let's look at the zinc ion. In the zinc ion, now notice that we've lost the 4th shell. So now shell 3 is valence. And so if you look at, it's only shells 1 and 2 that are my core electrons. So if I look how many core electrons my zinc ion has, it only has, what, 2 plus 8. It's just got 10 core electrons. So its effective charge is going to be, it looks like it's going to be +20. Woo! It's going to be much higher. And then in your shells, the valence electrons in zinc are shell 4. Zinc ion, they're now in shell 3. So I definitely expect my zinc +2 to have the greater ionization energy, because when you're removing an electron now, we've got 2 things happening. One is it's closer to the nucleus, and then also it's experiencing a greater effective nuclear charge. And that's because there's less shielding happening there. In your zinc ion, right? Because we've got fewer core electrons now in the middle, because we've kind of bumped down a shell there. So you want to say zinc has a greater ionization energy. Justifying your answer, you could say because this one, zinc has valence electrons in the 3rd shell versus the 4th shell, and so they are closer to the nucleus. They experience, less shielding. Those things are going to combine to make them more attracted, which makes them harder to remove from the atom. All right, let's look at this one. Sulfur and S2 minus. So sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. The S2 minus ion, remember, when you form a negative ion, that means you gain electrons. So what we're going to do is we're going to add those 2 electrons to our valence shell. We'll find we're always gaining and losing from the valence shell. And then it tells us that the S2 minus has a larger radius. And so we want to explain why. Well, we could, make a T-chart again. We've already got a comparison of their electron configurations. They're both sulfur, so they both have 16 protons. So the protons are the same. So if you look at that, and they're both got electrons in the 3rd shell, they're in the 3p. The only difference between these two is that the sulfur ion has more electrons in its 3p than the sulfur atom. So that must be what's causing this difference in radius. And so what we would say is that the S2 minus ion has more electrons in the 3p, and you've got the same number of protons attracting those in. That's key to be aware of. So when you have more electrons, you're going to end up with more repulsion. And then that electron cloud is going to kind of spread out. So you're going to increase the, distance between those valence electrons as a result of that repulsion. So that's what's going on when you form a negative ion. All you're doing is adding electrons. Number of protons stays the same. So those extra electrons just repel each other and then make that electron cloud spread out. Therefore, you got a bigger radius. So now let's compare the S2- ion with argon. So S2- and argon, when we compare it, can be helpful to make a little T-chart here. So they have the same electron configuration. Let's write that out real quick. 3s2, 3p6. So same electron configuration. The only difference is sulfur has 16 protons, argon has 18. Remember, what identifies the element is how many protons it has. So 18 protons means argon. That's the definition. I'm getting this number from the periodic table, right? So from which one is it easier to remove an electron? Well, it looks like S2- has, fewer protons attracting those electrons in. So it's going to take less energy to remove electrons from the sulfur ion because sulfur's valence electrons are less attracted to the nucleus, right? They're experiencing a weaker effective nuclear charge. We've got, 16 protons versus 18 protons. So there we go. Let's take a look at this one. So some more compare contrast one. And notice how when you're answering this type of question, you got to make sure you refer to both substances. That's where making a T-chart can kind of help you out. So lithium, beryllium. We look at their effective charges. We'll see that lithium has an effective nuclear charge of +1. Beryllium's is +2. They both have their valence electrons in the second shell. So the reason why lithium has a larger atomic radius is you could say they have they both have the valence electrons in shell 2, but lithium experiences a weaker effective nuclear charge than beryllium does. So therefore, it's not going to hold his electrons in as tight, so it ends up with a larger radius. Let's look at potassium and calcium. So this one asks us to look at the second ionization energy of potassium versus the second of calcium. So the way ionization energy works, the first ionization energy would be the energy to remove one electron and form a +1 ion. The second ionization energy would be the energy to remove an electron from an ion, from something that's already lost one. So basically I'm taking the +1 ion and I'm turning it into a +2 ion. That's the second ionization energy. Same thing over here with calcium. So what I want to compare is I want to compare the amount of energy it takes to remove an electron from the K+ ion and the Ca+ ion. So if I make a T-chart, I want to make sure I compare the +1 versions of each of these substances. Because again, I want to compare their second ionization energies. All right. I'll write these out for both of them. Okay. So the K+ ion has this electron configuration. It's neon 3s2, 3p6. Looks just like argon. And then calcium's is argon 4s1. Okay. And then the effective nuclear charge, if you look at it, potassium has, let's see, 19 protons. And now it only has 10 core electrons if you look at its electron configuration. Because now its valence shell is shell 3. So it looks just like argon. So argon has 10 core electrons, so does this ion. So it's got an effective charge of +9, which is pretty darn big. Over here in your calcium, though, calcium has 20 protons, so it's got more protons, but it also has a lot more core electrons. It's got 18 core electrons. So its effective charge is +2. So notice that potassium has a greater effective charge and its electrons are in a closer shell. So that's why it has a greater second ionization energy. So it's got a, potassium has a larger effective nuclear charge than calcium, and you would be, removing electrons from shell 3 versus shell 2, sorry, versus shell 4, the opposite. So as we are, closer to the nucleus, is going to be more attracted, harder to remove. I'm not writing down every word I'm saying, but that's how you want to explain it there. So make sure you clearly mention both things. That's why I think T-charts can be helpful, so the reader can see that you're comparing these things. What you want to avoid is an answer like this. If you write down because it has more shells, that explanation would receive no credit because we don't know who it is, right? Is it calcium? Is it potassium? And also, why does having more shells? Explain the observation. So make sure you clearly mention both substances, make a clear comparative statement in your response there. Let's look at one more here. So this first one, write the equation for the ionization of fluorine that requires da 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 da. So a lot of people get confused by this wording here, but notice here it says first ionization energy and it has a value for it. So basically it's just asking you to write out what do we mean by first ionization energy? And the first ionization energy is the amount of energy it takes to remove an electron from an atom. So that's what this question is asking you to do, is to show that losing one electron. Okay, and then I'm going to try and account for the fact that fluorine has a greater first ionization energy than oxygen. Okay, so again, if you look at fluorine and oxygen, they're in the same row, so they both have their valence electrons in shell 2, but oxygen has an effective nuclear charge of +6, whereas fluorine's +7. So you would want to mention something about how electrons are both in the same valence shell, but fluorine's valence electrons are experiencing a greater effective nuclear charge. That's why it's got a greater first ionization energy, because as the first ionization energy will increase as you increase the attraction to the nucleus. And remember, when we're thinking about attraction to the nucleus, we want to think about those two variables there. Think about Coulomb's law. It's force over, sorry, not force, charge over distance. So in this case, the distance part is about the same as if they're both in shell 2. They're in the same shell location, but the effective nuclear charge is what changes. So fluorine has a greater effective nuclear charge. Therefore, its electrons are more attracted to the nucleus. Therefore, it's got a higher first ionization energy. And then you want to make a prediction for xenon. So xenon, if we look at it, it is way down in, let's see, 1, 2, 3, 4, 5. It's down in shell 5. So its valence electrons are in the 5th shell. And it has an effective nuclear charge of +8. So if we're taking a look at this one, I would, it's got an effective charge that's greater than fluorine's, but they're pretty close, +7 versus +8. Those are pretty similar numbers. And we see a dramatic difference in the shell location. So its electrons are much further away from the nucleus. So we would predict that this first ionization energy for xenon would be lower because what they have is they have a, similar effective nuclear charge, but xenon's valence electrons are in a much larger shell. We're talking about shell 5 versus shell 2. So they're going to be further from the nucleus. And that's going to make them easier to remove. Because remember, if you think back to this relationship, as you increase the distance between two particles, the attractive force decreases. Therefore, they're going to be easier to remove. All right. Thanks for listening.